Bad web docs create bad retrieval. I'll use Firecrawl and Python to crawl a doc site into clean Markdown and metadata, so your RAG index starts with usable text, not scraper junk. This is the pattern you'll be able to implement by the end, which crawls a doc site and turns pages into clean Markdown with helpful metadata. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Many teams grab HTML and shove it into an index. That gives you noisy text, weird headers, and broken code blocks. Your retriever then prefers markup quirks instead of helpful sentences. Firecrawl solves that by returning cleaned Markdown and basic metadata. So your RAG pipeline starts with readable content you can chunk and attribute. The intuitive goal is simple. Turn a doc's URL into plain Markdown. Split that Markdown into small pieces. Score and pick the best pieces for a query. The strength is speed and hygiene. The weakness is that you still need a good chunking and scoring policy for precise answers. We will build a small end-to-end baseline. First, we test scraping a single Quickstart page for clean Markdown. Then we crawl a route, split pages into chunks, denoise code, and assemble a tiny RAG answer with sources. That way, the code feels like a clear recipe, not a mystery call, before we run it. Now we verify extraction for one page. This snippet verifies Firecrawl's Markdown extraction by scraping a single documentation page. It sets the API base and builds an authorization header from an environment variable. Then targets the Quickstart URL. A post request to Firecrawl's v1 scrape endpoint asks specifically for the Markdown format, returning cleaned content that excludes noisy HTML boilerplate. The variable MD1 holds the extracted Markdown string, which is easy to index for retrieval tasks. Finally, the code prints the character count to confirm we received substantive, parsable text. The printed character total indicates whether Firecrawl returned usable, clean Markdown ready to seed your RAG index. Next, crawl a small set of pages from the doc's route. This example uses Firecrawl to crawl an entire documentation route and return multiple cleaned pages. It calls the v1 crawl endpoint with a small limit to keep runtime nimble while still proving coverage. The response is normalized into a list of dicts named pages containing a URL and its Markdown. Empty items are filtered out to avoid polluting your index with junk. Finally, the list is sorted by URL for deterministic ordering and easier downstream processing. Increasing the limit fetches more pages at the cost of time and bandwidth. The printed count shows how many clean, usable Markdown pages you now have for indexing. Now we split that content and try a cheap relevance score. This code chunks the crawled Markdown into paragraph-sized pieces and ranks them by a simple query match. The variable chunks store small text units paired with their source URL to preserve traceability. The function score computes a light relevance score by counting overlapping words between the query and a chunk, scaled by chunk length. The code then finds the best chunk for the query and calculates its score for quick feedback on retrieval quality. Shorter chunks can boost precision but risk missing context, while longer chunks can smooth scores but dilute focus. The printed URL and score show which chunk appears most relevant right now. Next, we remove code noise and compare results. This snippet denoises the chunk set by removing fenced code blocks before rescoring the same query. The function noCode walks line by line, toggling a flag when it sees fenced code block markers, and keeps only non-code lines, which often contain the explanatory prose most useful for RAG. It then creates CCH, a cleaned variant of the chunks list, and finds the best scoring chunk using the previously defined score function. By eliminating code noise, term overlap with the query tends to increase, or at least become more semantically focused. The printed score reflects how denoising changes relevance, indicating cleaner content may improve retrieval. Finally, we assemble a tiny RAG answer from the top pieces. This example assembles a tiny RAG baseline by selecting the best cleaned chunks and composing a short answer. It sorts the denoise chunk list using the same score function, keeps the top K results, and concatenates their text into a compact snippet capped at 280 characters. The set of source URLs is then extracted to provide simple provenance tracking for downstream display. Increasing K broadens coverage, but may dilute precision. Decreasing K sharpens focus, but risks missing context. The printed answer length and source count confirm you produced a concise, attributed response from crawled Markdown, forming a minimal end-to-end baseline. In short, Firecrawl provides clean Markdown and metadata for reliable retrieval. Use this when you need readable, attributable documents from messy doc sites. One caveat: the quality still depends on chunking and your scoring policy. Next step: scale this baseline by adding an approximate nearest neighbor index for your chunk vectors, and tune the index parameters to balance recall and speed. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.